ISPC, good morning, everyone. I'm glad y'all are all here. All, what, 28 of you now? That's pretty good. Um, ISPC is a nonprofit, as I'm sure most of you know. If not, I'm going to remind you of that. That being said, we are able to offer free webinars as part of our mission to promote safety in the power line industry. But occasionally we have to just remind you guys that we're a nonprofit and tell you that we have a way to donate directly to us, tax deductible, obviously. At the very top of the chat is a link to literally all that will show up on your screen will be a button that says donate. And then you click that button and you can donate whatever amount you want if you want to. And I'll send you a letter for your taxes. So that's all that I really have to say. Now I'm going to hand it over to Tony for the next hour. And then if anyone has any questions, you can put them in the chat box or in the Q&A box. And I will just interrupt Tony with your questions as they happen. And he'll answer them for you then. So I'll hand it over to you, Tony. I'm going to go quiet for a while.
Thanks, Jamie. Man, welcome everybody. Electric awareness for communication workers. We've done a lot of this training through the years for a lot of the telecommunication companies. The sad fact is a lot of times we had to come in after someone has been injured. So we love to focus on safety in the beginning and try to work on trying to get line workers and telecommunication line workers trained and knowledgeable so that they don't get injured. I've been doing electric line work for about 45 years now. And so basically what I'm saying is I'm old. I just discovered a couple of weeks ago, I have a cataract in one eye and one starting in the other eye. So that just shows the age. So I'm sitting a little bit closer to the computer because everything is kind of cloudy now. Anyway, this is actually a 3-day training on site. We come and spend 1 day in the classroom, make sure everyone knows all the principles and understands everything that they need to know knowledge wise. And then we actually go out in the field and, we show how, bonding to grounds, getting into the workspace, close to the electrical conductors and things like that. So we actually go out and get in a bucket or climb a pole, whatever, and actually do some of the proficiency training that OSHA requires. And I'll talk a little bit more about that in a little while. All right, it worked. There it is. All right, just like the pig in the trailer, a lot of times we just don't know what we don't know. Sometimes as a line worker, you feel like the pig in the trailer. I'm going somewhere, but why am I going there? And what is going to be the hazard? Well, I'm going to be lunch. All right, you'll see I'll go through a lot of these slides. I've done it in 3 hours and we've condensed it down to an hour. So I may go through a lot of the slides really, really quick. And so, if you want to see something, just let Jamie know, go on to the chat and ask any questions you may have. One of the things that I found out going through to a lot of companies and doing training is documentation of their PPE. There's a lot of folks that they come to work, we tell them, be here on time, drive safely, and learn to climb, be safe on the ladder and things like that. We give them a hard hat, safety glasses, and say, go therefore and be safe. But OSHA says we need to train our folks when PPE is necessary, what PPE is necessary, how to put it on, take it off, care for it. And all of that should be documented. There's just a lot of companies out there that don't document that. And I'll just say I didn't get a chance to look and see who registered for this. So I don't know who's on the web today, but thank you for being here. And I'll cover a little bit more toward the end. 1910-268, that's where our telecommunications OSHA regulations come from. I always give the folks a little OSHA snapshot so that they know, what OSHA is saying about safety with our jobs. PPE, protective devices, special tools needed for the work of employees shall be provided by the employer. And before each day's use, the employer shall ensure that those personal protective devices, tools, and equipment are carefully inspected. So how often do you inspect your hard hat? Before use each day, things like that. So when I'm on site, I spend a lot of time with the guys, getting them to know and understand what PPE is necessary and how it works. Hard hat, safety glasses, FR clothing. A lot of telecommunication guys don't get into an electrical zone, and we'll talk about what those distances are here in a little bit. So they may not need FR clothing, but anytime there's a risk of an arc for what they're doing, they should be wearing some FR clothing. Of course, boots to protect the feet, and then underclothes. If you are an electric line worker and you're wearing FR clothing, you can't wear, neoprene, different kinds of underclothes that may contribute to a burn in an electric arc. 1910-268C talks about training for communication workers. And basically it just says that the employers are responsible for training the employees. This webinar, like Jamie said, it's a free webinar. We have a sponsor, and we appreciate any donations as well. But our sponsor is our sister company. ISPC is the non-for-profit company, and our sister company is T&D Power Skills, which is the training curriculum. And I'll just read this to make sure I don't leave anything out. T&D Power Skills is a comprehensive line worker training program that focuses on electrical line worker principles and telecommunications. We have a telecommunications package as well. Safety related work practices performed in the field. Apprentices, journeymen, line workers in between will benefit from T&D Power Skill training units. The program is designed to engage the trainee in real life procedures and experiences. Consists of videos filmed in 4K, supported by vector illustrations and 3D animation, which is getting much, much better. We love our new units. Companion workbook that we suggest everyone has. We have our different learning styles. Some like to read, some like to look at the videos, some like to read while they're looking at the videos. And the workbooks always provide a good reference for later on. I don't remember exactly what they said in that video. Well, I can go to the workbook and reference that. The workbooks feature, just like you have here, OSHA regulations snapshot. So, we want the line worker to know what OSHA is saying. How is that keeping us safe? How does that relate to why I have to do this? Why do I have to wear my hard hat straight and not backwards? Things like that. And then we have field performance requirements, which each unit has, like for instance, climbing wood poles. You can't just learn how to climb a wood pole by sitting in a classroom. So you learn all about the equipment for climbing poles, all about safety, all about inspection. And then we actually go out into the field. We inspect all of our tools. We learn how to measure them, put them on correctly. And then we learn how to use proper techniques to climb poles. So that's the proficiency portion that fulfills a lot of the OSHA language in their training. Pre-tests can be designed by the administrator. Segment quizzes appear throughout. So each segment is about 4 to 6 minutes in the video. So it really helps, break it up. Our busy adult learners now, you may watch a segment or two, take a segment quiz. You can get out of the unit and then come back the next day and finish up. So it's really broken up into small chunks of time for our adult learners. The benefits of the line worker training program system include reduction of learning time, consistency of delivery, better understanding of line worker safety, skill development monitoring, a training documentation system, and the ease of remedial or refresher training. It's 78 units. It covers basics, your pole climbing, your basic electricity, introduction to the T&D system, things like that. And then we have overhead de-energized, which like framing poles and things like that you would do de-energized. And then we have an energized work cover up, changing out transformers, running secondary services and things like that are energized. Then we have several transmission units and substation units as well. The 78 units represent the major components of line worker career tracks to become a journeyman lineman. And the entire program can be purchased. So for more information, you can dial 318-880-2259. And there's also a website that you can go to, and I have that website on my last slide. So when I get to the end, we'll be able to see that. So that's a little plug for T&D Power Skills. We at ISPC work as subject matter experts to make sure that everything is in compliance with the telecommunications and the 1910-269 line worker, electrical workers, safety rules, and things like that. All right, some of the safety hazards for line workers. Doesn't matter if you're telecommunications or if you're a line worker in the bucket working on energized. We have energized conductors, current flow going through the person and the ground. So basically what this slide is showing is 2 points of contact, okay? You can touch the ground and touch something else that's at the same potential grounded, and there's no problem. You can touch something that is electrical and energized if you are insulated, but if you touch that second point of contact, which is grounded, then you'll be in trouble. So that's just the 2 points of contact. On site, we spend a whole lot of time talking about the basic electric theory, current, voltage, resistance. We'll go by the Ohm's law. That way, we know a little bit, they understand especially when I start talking about grounding and bonding and voltages and currents traveling through your body, induced voltages and things like that. If you don't have any electrical theory background, it's hard to understand what that is. So again, step and touch potential. We spend a lot of time actually talking about the step and touch potentials that guys have a risk to them out in the field. So, they may have a ladder that's up on the telecommunications line and, 4 or 5 feet away from the system neutral. Are they still at a risk? Anytime they touch the pole or any of the communication messenger wires that are bonded to the pole, they may be at a risk. And I'll talk a little bit about that, but that's where most of our training actually goes for. So what are hazard levels from electric current? And basically it's 50 milliamps. If I can get 50 milliamps, which is 0.05 amps, much less than an amp. So if I can get less than half an amp flowing through your body, I can actually stop your heart. Now, how can I do that? Well, I have to get some voltage to penetrate the skin. Charles Dalziel is the one that came up with all these tests. Let go thresholds, men are maybe about 76 milliamps, women 51 milliamps. Muscle control loss, men at 90 milliamps, women at 60. Ventricular fibrillation, men and women usually about 500 milliamps, and that's what we're talking about. And then the high voltage occurs at 50 watts per second. So basically what we're teaching them there is you can't know that electricity, you're not quicker than electricity. It travels very, very fast. Some of the facts about some of the electrical hazards, Dalziel's tests show that the flow between 10 and 21 volts AC in your hand and salt water and copper plates gives a pretty good current, can create a pretty good current flow. 500 ohms commonly used in all of his assumptions. We spent a lot of time talking about all of that. And then knowing the difference between DC and AC. So I've hit a lot of slides in here that would take up a lot of time for doing this, but AC is created by the movement of a coil of wire in a magnetic field. That magnetic field moving around the coil of wire, the coil rotates uniformly through two opposite poles. This becomes very important when we start talking about induction and how induced voltages can create a hazard onto a communication messenger wire, or grounding. If you're going to ground, like say a splice box underground or on a pole, you may be getting at some, or at least close to some kind of risk. Generation of three-phase electric power, all it is like three different brushes that are spinning. All right, so that's how we get three separate phases, which, by the way, are not simultaneous, but sequential. So that's why we have it at 1, 2, 3. And kind of important when we start talking about grounding, and I will not have any time to talk about grounding here. I'll just basically mention a little bit about it. All right, the electric field around a conductor is real. It can jump outward when a conductive object comes too close. Now, how far can it jump? A lot of it depends on the voltage, the amount of voltage, the amount of current that's flowing in the line. This field can also cause conductive objects within the field to become energized. So we make sure that they know and understand and try to be able to determine for themselves when an induced voltage might be creating a risk to them while they're working. Even a pole ground, the copper ground wire coming down the pole, there's amperage always flowing on it because there's a return current. So in the electric line, there's a return current on the system neutral. So what do we bond the system neutral to? The pole ground at just about every pole. So what do we bond the messenger wire to? The ground, which is bonded to the system neutral, which has current flowing on it. Now, how much current is flowing on it? It's usually, I say usually grounded because things happen out in the field. People steal copper and things like that. So they're usually grounded, which dissipates the voltage off of it, but the current is still flowing into the earth. If you can get it at a different potential, you might receive a shock. All right, so induction is caused by the magnetic field around the energized circuit. It weakens as it radiates outward from the conductor. So at 18 inches from the conductor, you may get a charge. And you can feel it. At 24 inches, you don't feel anything. So it drops off as it goes out. And we usually spend a lot of time trying to get the folks to understand how that works. We spend a little time trying to identify what is in the utility system from generation to the customer. So, I would spend a lot of time on this map, but you can see we produce electricity. It goes to a substation, goes out, reduces back down to a distribution voltage level, and then reduces down through a transformer to feed the house. Transmission usually looks a little bit taller, a little bit higher. Distribution on the right-hand side usually has a little bit smaller insulators to it. And then the secondary, that's usually the biggest exposure for your workers, 120, 240, sometimes maybe 277, 480, which is a very hazardous voltage in itself. So if you had a guy that had to climb the pole and run a service off of this right below that light, the little street light presents another risk to the worker. Sometimes the grounds are not bonded real good. And if the pipe is not grounded, it could actually hold voltage while the light is on. When the light is off, it usually doesn't have any voltage to it. But like I say, usual. Is it a risk? Yes, it is. All right, so then we spent a little time talking about sectionalizers, reclosers, cutout fuses. A lot of times, when you hear the explosion, like a rifle going off, a lot of people say, "Oh, the transformer blew," but actually, it was not a transformer; it was the fuse. And basically, it's just a small piece of wire going through as it overheats from an overvoltage or an overcurrent relationship. It would blow out the bottom of the barrel. So there's another hazard to your guys. They're working on a pole. Have the ladder, so they're not even touching the pole. They may be 3 feet away from the pole. But if there's a cutout right above them and there's a fault on the line that makes that cutout blow, then it's going to shoot out some gases underneath and probably some little shards of metal from the fuse blowing. So there's another hazard. Capacitor banks. Um, the big hazard with the capacitor banks is grounding. They actually hold a charge, and they help increase the current that reduces the effects of motor load. So, for instance, if you had 7,000 volts on a single phase line, and we had 6 or 8 motors, like maybe a dry cleaner or something, 6 or 8 motors going, it would actually drop the voltage down a good bit. So a capacitor actually helps increase the amperage, the current on the line, so that the voltage can stay up for regular customers. Reclosers, we talked to the guys about reclosers because if a fault occurs on a line, a recloser may open up at some interval. Every company is a little bit different, but at some interval, that recloser is going to come back on. And if the fault is still there, it may go out again. And, every company has a different scheme. Some are 12, 15 seconds, some are 30 seconds, but the recloser will come back on. If the fault is not cleared, then it will open up. But your guys need to know that if the line goes out, if the main feeder line goes out, it may come back on. If a car hits a pole and the conductor's laying down on the ground, they're not necessarily de-energized. A recloser may have just seen the fault and then would re-energize those wires. So we spend a lot of time going through that, time that I don't have here. Surge arresters, another risk to our communication guys. You can see it hanging off the side of the transformer. The bottom part is grounded, the top part is energized, and we call them lightning arresters or surge arresters. So if there's an over voltage incident, like say transmission phase wire falling into a distribution wire, or if lightning is in the area, these try to protect the equipment by taking all of that energy to ground. However, there are discs inside of many of these surge arresters. So when a lightning strike occurs, those discs usually explode out the bottom to try to protect the equipment. So there's another risk to your guys. Distribution 3-phase. Here's 15 kV insulators. I can tell because of the size of the insulators that are on top. And 15 kV and lower is a typical distribution voltage. There's many cities that would run a 25 kV, so it'd be a little bit higher. Here's a recloser. So I'm just going really fast because I have a lot of slides to show. So you can see the primary phases. This is a Y system. So a Y system has your 3 primary phases on top, and you can see right about the top of that transformer, a system neutral that is connected. You can't really see it where it's coming back to us, but going off right to the left, there's a little spool that's right there. So a Y system has a system neutral. And like I said, the system neutral is a return current carrying grounded conductor. So the secondary coming out of the transformer, the neutral in the secondary is also bonded to that system neutral. So the current returning back to the transformer from the customer is also carried through that transformer and bonded onto that system neutral. So usually about this time, I'll start getting a lot of questions from my class as to how come we haven't been electrocuted in the past. And I will say this, I have talked to some telecommunication workers who have been shocked. And the reason they didn't get killed is it probably wasn't enough voltage to penetrate their skin so the amperage could flow. So are you at a risk if you get shocked? Yes. If I can penetrate that skin, which takes about 50 volts on average, then I can send that amperage through you. This is a three-phase distribution sectionalizer. This sectionalizer is actually energized. So the insulation, keeping it separated from the pole, is actually in the hanging bracket. All right. 120, 240 volt service conductors, sometimes maybe 277, 480, depending on the size of the customer and the voltage that they need. But we call the 2-wire a duplex, the 3-wire where you have 2 conductors and a neutral, a triplex. And then if it's a 3-phase, you have 3 conductors and the system neutral. They usually bond to the pole. I have the picture on the left showing how we bond that secondary neutral to the ground wire coming down. So is there a current flow coming down that pole? And yes, there is. We have at ISPC, we also do a lot of investigations, being in safety for so many years. I've done a lot of investigations. So we usually have, when we have time in the classroom, I go through some incident cases and talk about how people have been injured and killed, by touching a ground. Okay. We don't have a lot of time now, but you can see on the right-hand side, that's that same picture I showed earlier. You can see how the system neutral is tied to all of those neutrals, and then you have one wire that's going back to a transformer from there. A lot of your typical single phase is about 7,200 volts, 7,600 volts in some companies. It just depends on what the company is using. The open wire 240, you see the line worker on the bottom. Just to the right is an open wire secondary, which means it does not have any insulation on the conductors. So that is energized at 120 volts. If he was on that pole and reached over and touched one of those wires, we have over 50 volts. We'd have enough power to actually penetrate his skin and injure him. So we cover a lot of that while we're in there. 3-phase delta circuit. All right. On the left-hand side, you can see we still have our 3 conductors up top, but what's missing is the system neutral. So a delta system does not have a system neutral. Therefore, any return current will go down every transformer, every piece of equipment that has a ground wire going down the pole. That return current is going back through the earth. So, the question again, why don't we get shocked? And because if we have everything grounded, we have collapsed any voltage that may be on the line. However, if we have a situation where one of those energized conductors falls onto the system neutral or falls down onto a ground, the system protection devices that I'll talk about in a few minutes, they will trip as fast as possible because it is grounded. However, there will be an energy situation briefly while on that line. So if I'm a telecommunication guy. I'm standing on a pole, I'm hooking up a service, and I'm touching that ground wire. Would I get electrocuted? And all I can say to that is the risk is very high. All right, 4-wire Y circuit. You can see the system neutral. It's not real clear, but you can see the system neutral right behind the transformer. It's actually on the other side of the pole. And then the picture on the right is a 3-phase delta system. So there is no neutral. All of the return current coming from that building on the right that you see is going to go through that transformer to the ground and down to the earth. Okay. Single bushing transformer connected to a 4-wire Y circuit. It's kind of an older picture, but you can see the neutral at the bottom of the transformer. And we didn't get a real good shot of this. It's kind of an old picture, but you can see the communication wires at the bottom, and they look like they're fairly close to those secondary connectors. A single bushing transformer is energized at the top and grounded only through the case ground. That's why we have that picture on the right hand side there showing that case ground. If that ground wire is not connected, then that unit will be energized. At what voltage, it's hard to say, but could be as much as 7,000 volts. And the bracket right there that transformer is hanging on would also be energized. So we've had instances in the past where that ground wire came off, it energized the transformer or the bolts that are going through the pole. It actually burned a hole in the pole, and the transformer fell off of the pole as the bolts heated up and burnt the pole in two. So there's a lot more hazards out there than a lot of our guys think about. So, I just threw some extra pictures in there to try to help the guys identify what voltages, what type of insulators. These are polymer insulators, so they're not the glass porcelain, and they're usually rated, this size is usually rated about 15 kV. However, they could be rated at 25 kV. So, different companies have the different voltages, and I'll talk about the minimum approach distances in a little bit and why that's so important. Here you have the transmission conductors that are over the top of distribution conductors, like I mentioned. These are standoff bushings, standoff insulators, and the clamp in is not in the center where that shows. I can't remember where I got this picture from, but the clamp in is actually out on the outer end of that. Here you have the insulators with guys backed up to a angle pole. Just some different circuit configurations. All right, y'all get to get a break from hearing me talk because I want to show this video.
Yeah, that's live wire. There goes the transformer, Blue.
There goes the electrician.
And the transformer did not
I said,
blow.
somebody call NLG&W.
Yeah, 911.
911.
That thing's live, isn't it? Look how live it is.
It is live.
All right, I paused it right there. You can see on the pole, there's 3 transformers. So there's 3 separate fuses. The conductor fell down, and you see it laying on the ground and nothing happening. So basically, it did not create enough fault current to cause the recloser to open up. Well, the wind blew, and you saw where one of the transformer fuses blew. So it actually went phase to phase, created enough current to trip the recloser. So now the line is laying on the ground, probably de-energized, and then you see it light up again. That's that recloser closing back in, energizing that line again. However, the line just laying on the earth like that is burning, but it's not creating enough fault current for that recloser to see it. So you see it continuing to burn for a little while, and then the wind blows again. You kind of see it through the bushes and the trees, and finally it goes phase to phase with those other transformers. The recloser actually saw it 3 times just because of that phase to phase fault there. So then it eventually goes out, but you can just see what the risk is. So I usually get a question in here: what if a car drove across that line while it was energized? Well, there's a lot of different things. There's usually enough rubber in your tires. If you had bald tires, the steel core that's in the tires could actually energize
And that's
that
more than
wheel.
115 volts.
So there's a risk for people.
Bird?
Anyway,
It depends on if it crosses lines.
During this, you can see that no one drives across it, but here it is, energized again.
Yeah, I saw it fall from, it came loose from that pole there.
So there it just went phase to phase through that 3-phase transformer. So now you see all 3 cutouts are hanging down, but is the line de-energized now? I don't know. It depends on the company's scheme and how many times they want to trip the recloser. You can see, if I can get my cursor up there, that's where it came apart. So the conductor came apart right there and fell on the ground. That's why it was burning here and here. So at the end, you can see the line worker pulled up in the truck, put a couple cones out to try to mitigate the hazard. All right. Here we have too fast, Tony. Here we have a regular panel circuit breaker that's in your house. So I talked about reclosers and circuit breakers. So the circuit breaker on the system and recloser on the system will trip back, but it trips because of fault current. In your system in the house, you do not have any return current on your neutral. And it's designed that way because we don't want a risk to our folks in the house, plugging in an appliance or touching anything that may be grounded, grabbing a lamp, things like that, changing out a light bulb. You don't want any amperage on that line. So your house is designed where there is no return current on that system neutral. So the recloser on the right, or circuit breaker, will have return current coming back towards it on the system neutral. So not that your guys would ever be in a substation working on equipment or anything like that, but I just wanted to kind of point out the difference right there. So the difference between a recloser and a circuit breaker: many circuit breakers do not reclose, they just trip the one time. Recloser, I think I've explained that well enough. So in the substation, here's just some different equipment. You can see the primary, how high it is off of the ground, some transmission breakers, the size of the insulators and things like that. So what you saw in that video was one fuse holder went out, and we started single phasing the customers off of the 3 transformers, and then the other 2 fuses blew. Did it make it safe? Well, if the energized line came back on and there was nothing to show any fault current back to the recloser, it would not have tripped again. So what you just saw was a 15 kV rated cutout barrel, cutout assembly. And here is a 25 or 35 kV. So you can just see how the whole body itself is a little bit larger. The fuse is a little bit longer. So the higher the voltage, the more insulation we actually need. Here's just a typical guy putting in a cutout on top of a transformer from off the pole. Here is another video. I tried to break these up where y'all didn't have to hear me talking for the whole hour.
That's electricity running up the flames. That's cool. I'm doing video, yes sir.
The big question I usually get here is how come it didn't trip out? Well, again, we're not creating enough fault current for that recloser to see, but we did create enough heat that it eventually burned the line down. Gets a little confusing there. We did create enough heat to actually burn the line down so that the recloser did finally see it when it went phase to phase, and it opened up. However, if the conductors laid on the ground were not in contact with each other, that recloser could very well come back on again and energize that line. So that's when people really get injured, assuming that when a line falls on the ground, it's no longer energized, but that's not the case in most instances. Minimum approach distance, understanding the reach, the extended reach, and how to measure the approach limit are the minimum approach distance. So basically what we're talking about here is your communication guy might be on a ladder next to a pole, and if he can physically reach up and touch that system neutral, then he is in the minimum approach distance. Now, should communication guys be wearing gloves? No. If you're going to start buying rubber gloves, you're going to have to start doing rubber glove training. Rubber gloves get tested every 6 months. An extreme cost to your company. But we do need to be aware of where we are on the pole. I do know that there are some utilities or municipalities, co-ops that may not exactly follow the National Electric Safety Code in distances. Communication wires may be a little bit closer to that neutral than what the National Electric Safety Code tells us it should be. So we may be at more of an exposure than we think we are. Should your guys have some cover up? And I think maybe so. There's some inexpensive plastic cover up that's on the market. And they could actually apply that with a hot stick, so they wouldn't have to get any closer to it. But it would actually create a little bit of a barrier so they don't touch that system neutral. All right, moving on very quickly, talking about the minimum approach distances. How do we get these numbers? It came from the IEEE 516. Cover up is rated and tested for the voltage at which the worker is using. It's used to replace the air gap insulation between the worker and any energized parts. Covering distribution voltages. I love this picture. I talk about this picture with my line workers a whole lot. Pictures and angles show a lot of different things, but the line worker on the left inside the bucket is still exposed. They put one line hose on the conductor. There should be another line hose there because he can't reach the line with his head, but he can actually reach it with his hands. So, proper cover up is always very important, and we spend a lot of time on that. Here's some of those distances. This is out of the 1910-268. 1910-269 is a little bit different. It just adds a couple more inches to it since 2014. OSHA has not really had a chance to go into here, but 750 volts to 2,000 volts is about 18 inches. Over 2,000 volts up to 15 kV is 2 feet. Now, the question I usually get here is, all right, Tony, you're saying 2 feet. Is that the energized conductor? Well, the neutral is a current carrying grounded conductor, hopefully grounded. If you hadn't had any copper thieves in a while, maybe it might be grounded very well. So do I have to be 24 inches from that system neutral? OSHA says, yes, you do. All right. Communication workers may only encroach closer than the distances if the employee is insulated or guarded from the energized parts. Insulating gloves rated for the voltage involved shall be considered adequate insulation, or the energized parts are insulated, are guarded from the employee by other conductive object at a different potential. So we're talking about some covering. The rubber line hose, it's a little bit difficult to put on and take off. That's why I kind of mentioned the plastic. It usually has, it's lightweight. It usually has a cover over where it covers over the conductor, but then it has a little plate that goes up underneath, a little plastic plate. So it actually just clips on, and then to take it off, you just pull it kind of at an angle to get it back off. I would suggest, if you work at a company or for, underneath an energized circuit that they may have encroached that National Electric Safety Code distance and are putting your guys at risk, I think I would spend a little bit of money and time and train some of those guys how to put and cover up those risks to your guys. We'll talk a little bit about rigging, digger derricks, and bucket trucks. I'm going to just breeze through this. There's a lot of pictures. If your guys are going to an existing anchor that is also backing up a energized conductor on the pole, there could possibly be some current on that guy wire that's coming down. And is it a hazard? Is it a risk to your guys? Not unless they have any differences of potential. So if we have a different voltage through, between the earth and that guy, then it could be a little bit of a risk. A lot of times our down guys where they're going through the energized conductors will have insulators in them and could be a risk to your guys. If they're also putting a guy and an anchor behind this pole and they actually pull the pole over a little bit, they could possibly sag a conductor and have it, sag down into the hazard, causing a risk. All right, anchors and guy wires. I have 10 minutes. We, just talking about the safety of putting up poles, bucket trucks. Outriggers on bucket trucks. I know most communication trucks do not have outriggers, but if they do, the outriggers shall be put down in sight of the operator at all times. Overloading buckets, bucket weight. A lot of times we put a lot of tools in our bucket and we may overload the bucket, so we should know what that weight rating is for the bucket. Hand lines, knot tying. A lot of our communication guys don't use hand lines, although they should. We should never be throwing hand tools up to a guy on a ladder or down to a guy on the ground. We should be passing them up and down on a hand line or at least a tag line or something. Some of our bucket trucks, the upper boom may be insulated or may not be. You see the white part in the middle of that lower boom. That's a secondary insulation for that truck. Non-insulated bucket trucks, which most of our communication workers use, even though it looks like it may be fiberglass, if it is not tested on a regular basis, electrically, dielectrically tested, then it is considered a non-insulated bucket truck, even though it may be a fiberglass boom. Grounding trucks. Most of our communication guys do not ground their trucks, and it's because a lot of times they drive while lashing cable and things like that. But we talk a lot about what some of the hazards would be grounding the truck, going to a ground rod, or going to a down ground wire that's coming down a pole. Creates another risk to the employee. 1910-268J talks about rules for mobile equipment. So we go through some of the bucket rules and some of the derrick trucks, the minimum approach distances, talk a little bit about that while you're in the bucket, things like that. Setting poles in line. I know we do have some of our communication companies will set an electric pole in line. Very hazardous. I don't know how we get away with it. All of those lines should be covered or de-energized and grounded before we stick a pole up in it. A lot of questions I get during this part of the program is, sorry about that, turn your phone off, but then your watch rings. All right. Handling poles. Wood is a conductor. We've done a lot of conductive wood tests just to show how many volts a pole can actually carry. Creosote poles, usually a little bit lower voltage, but our new pressure treated poles, they're usually pressure treated with some kind of chemical that has a metal in it, which makes the pole now very conductive. So anytime setting a pole, it should have at least some cover on it. I would never let any of my employees set a pole in line without uncovered conductors, energized conductors. All right, moving on. Weights of poles and things like that, handling poles. I cover a lot of the communication rules for handling poles. Trimming trees, employees engaged in line clearing operations shall be instructed. Pruning, trimming, removing, clearing trees. Just make sure you don't cut a tree limb that falls onto an energized conductor, and never cut the tree limb that you're standing on. All right. Direct contact is made when any part of the body touches and contacts an energized conductor. So even especially a green branch, as you saw in the video we showed earlier, green trees conduct electricity very well. What I didn't mention about that tree that was on the conductor, if someone would have went up to that tree to try to maybe push it back off of that energized line, they probably would have been seriously injured or killed. I know somebody that had that. I won't have time to cover that injury, the fatality now. But the law requires that a trained line clearance tree trimmer be used if electric hazards associated with tree trimming exists. Here I'll go into some of the underground stuff. We've got just a few minutes left. Just underground distribution, transmission voltages, what they look like. Here's some of the communication towers that I've taken pictures of out in the field. Here's one that I found. We're trying to hide our communications now. So we make it look like a tree, a nice palm tree. Here in Louisiana, there are several of these that they've made look like a pine tree. And they painted it brown, so it looks just like a pine tree. The limbs hanging out, they're actually metal, but they painted them green to look like pine tree limbs. Here in this slide, I just wanted to show how we, connect to the system ground with our communication, or the system neutral, I'm sorry, with our communications. whether you're working inside of a substation doing communications work. We've been to several companies doing training for them. And I did want to talk a little bit more about grounding before we go. That's actually the next 3 hours that the slide presentation has. One question I have is for you communication guys, how did this tower catch fire? I'm assuming it possibly got struck by lightning, but if that's not the case, I would love for somebody to maybe get on the chat and tell me how the poles catch fire. I know they radiate a lot of heat out of these antennas, but I've just never been able to get an answer yet as to how a pole would catch fire unless it was a lightning strike. All right, I said at the end I would put up the T&D Power Skills website, so you can go to sales@tdpowerskills.com and find out more information about our training packages that we have in there. We have a really good telecommunications training package. I've come on site to several communication companies and done what we call train the trainer. I've taken your trainers and made them aware of what the hazards are, and we've actually sold them the presentation so that they can go out and train all of your employees and hopefully keep everyone safe and secure. So next we talk about grounds, and what I get into is more of the intricacies of bonding the communication messenger wires underground especially, but overhead as well. Your communication messenger wire that is not bonded to the system neutral could possibly, all right, it's not a very high risk, but it could possibly actually acquire some induced voltage from the lines that are on top. And let me give a little bit of an example of that. I was at a technical college. We were doing some training. We had an energized conductor. The energized conductor I measured was 12 feet away from the training conductors. So there was just a couple poles that were set and some lines that were pulled in between. The lines were on insulators, so they were not grounded in any way. The energized conductors were going to several portable buildings. I think each building had 4 to 6 classrooms. So very, very large buildings. And I knew there was a lot of load that was going to come on that weekend because we had a cold front coming through. It was actually a dry, windy cold front coming out of the north. The training line was on the south side of that line. The line was 13,200 volts, 7,600 volts phase to ground measurement. And because the cold front came through, they had a lot of heat load trying to get those classrooms warm for the students. So it was about 9 o'clock in the morning. I got out and I got a voltmeter, and we actually measured the voltage on the lines that were 12 feet away from that energized line. So from 7,600 volts, the induction on our line was just about 14 volts. The center phase on our line had about 6 volts, and the field phase had maybe 1.8 volts on it. So that's induction from 12 feet away. The wind had a little bit to do with it, maybe taking some of the load and bringing that inductive load across to the insulated conductors that were up in the air. So anyway, I bring this point because our guys are working on those messenger wires, whether it's 15 kV, 13 kV, 25 kV. There could be some inductive load onto that. Now, if your guys are on ladders and just inadvertently touch, and I hope that they're on insulated ladders, not metal ladders, but if they're on an insulated ladder and they touch a pole ground, would they be shocked? And the answer is probably not. is the risk there? And I will say, yes, it is. If that messenger wire is not bonded to that pole ground, you could get a difference of potential if you're touching that messenger wire and reach over and touch that pole ground. So our guys that are actually out there stringing these messenger wires and latching cables, is there a risk when they're grounding or bonding that messenger wire to that ground wire? And my answer is yes, they are at a risk. Um, I'll finish this. My time is up, but I'll finish with this one last little scenario. There was a guy working on a line crew, young kid. Uh, the crew told him to ground the truck. They didn't have a temporary ground rod there. Rule was to go to the system neutral. The system neutral was not able to be accessed. It was a digger derrick truck. So they couldn't get up to the system neutral until the bucket got there. So the foreman told the kid to go to the pole ground. He went to the pole ground. He took a screwdriver. He actually pried the ground out and reached up with the ground, the ground from the truck in one hand and grabbed the ground wire in his left hand and got shocked. Went back and told his foreman, hey man, I can't ground the truck. I got shocked. And the foreman said, no, you didn't. It's a ground. It's impossible. Well, about that time, the system dispatcher called the foreman and asked, okay, what did you do? And he said, I didn't do anything. And they said, well, we just lost that circuit. Well, the same time that that kid touched that ground wire, a truck from about half a mile away ran over a guy wire. And when he ran over the guy wire, he actually broke part of the cross arm, and the conductor came down, landed on top of the system neutral. The system neutral energized that ground wire that was coming down the pole, and the kid got shocked. There was no real burn marks on his hand. He was wearing leather gloves, but he did actually receive a shock. So, are your guys at risk? And the answer is yes. Would you like for us to come and do some formal training? Now that our states are starting to open up, we are getting very, very busy. As a matter of fact, I will be out of the office for the next 3 weeks doing some training and already setting up half of June. So if you want us to come on site and do some communications training for your guys or a train-the-trainer for your workers, give me a call. There's my cell phone number at the bottom, Tony at ISPC. And, we would love to be able to work with you. All right, Jamie, I'm about done, I guess. Did we have any chat questions, Q&As?
Can you open your chat box? There's just a couple comments mostly. I
Okay.
didn't know if you wanted to speak to them. And then Todd McCabe wasn't able to hear us, so I'm gonna contact him after this myself.
Oh,
I'm gonna see if I can't get him something. He couldn't hear us the whole time. I don't know what was going on. I hope nobody else had that problem. I had it earlier, but I think we got it resolved. So
yeah.
I will speak to him privately. But Mr. John Frost had a couple comments I didn't know if you wanted to speak to. One about a house neutral and the grounding wire, and one about wind and inductive fields. Can you see them in your chat?
The chat is not open.
Oh, well, I'll read them to you. Earlier, it was about halfway through, you were talking about a house neutral. He said a house neutral definitely has current on it. The equipment grounding wire does not. And then a minute ago, he said wind doesn't affect inductive fields. So I didn't know if you wanted to expound on any of that, but I just wanted to let you know they were in there.
Well, it was actually the wind and the colder temperature, which made the inductive field grow because we had so much current that was on the line. So there was a lot of factors in there. And you are correct. Wind does not increase the inductive field, but it does help. A cool wind does help make the inductive field go a little bit further. And what it is, it's the drier air that and the increase of amperage. So there are a lot of different factors that are in there. We had talked about the house neutral. and it does not carry current. And that's by design.
Okay.
But
Well,
the breakers, I guess, that are feeding all of those are current related breakers.
Okay, well, that is it, guys. The biggest question I usually get towards the end of these is asking for a copy of the presentation. And yeah, we can't do that for the free ones, obviously. These are very, very shortened from a much longer. Tony will go into a lot more stuff. If you want to book him to do one of these for your guys, then just get in touch with us. But I know everyone got something out of it, and I hope you guys keep an eye on your email inboxes for next month's free webinar as well. So that's it. I hope everyone has a good day. You done, Tony?
Thank you, everyone.
Okay. Y'all have a good one.
All right.